Next talk is by Manas Mandal, who will talk about the cohomology of generalized Dold spaces.
First of all, I wish you Happy New Year, and today I will talk about cohomology of generalized Dold spaces. So mainly I aim to explain you an example of the paper joint work with Parmesar and Sankaran. So that will be only last two slides. I won't go too much in the details. So the main keywords in the title, as you have seen, is cohomology and generalized Dold spaces. So first we will have an idea of cohomology, and in cohomology there is a very nice symmetry in the cohomology groups that we will see using Poincare duality, and the another keyword generalized Dold space that we will see, and we will see another example also, that is a sphere bundle, and then we will try to understand the example there. So the basic thing in algebraic topology is that first you take a topological space and then we try to attach a algebraic structure to it. So cohomology is also part of algebraic topology, and here also we will do the same thing. First you take a topological space X, and then we attach a sequence of abelian groups, we denoted by H0, H1, H2 in that way. And then if you take all of them and make direct sum, so there we will have a multiplication, cup product, and that makes this H star in the direct sum of all the abelian groups a ring structure. And so why do we want this, why do we try to attach these algebraic structures to topological spaces? So sometimes studying algebraic topological spaces directly is hard. So even like two topological spaces are different or not. I mean, topological spaces are like somewhat whatever we see in real life, like chair, table, all these things are topological spaces. So everything, almost everything can be considered topological spaces. And so those things which we see, that we can easily distinguish that they are equal or not. But like in higher dimension, we don't see them. But there are also topological spaces, and we want to check that they are equal or not, in some sense that one can be deformed from one to another or not, continuous way, like without cutting and pasting. So that's why we need these algebraic invariants. So if for the like equivalent topological spaces, the attached invariants will be same. So if the attached invariants, algebraic invariants are different, then the topological must have been different. And here in this idea of cohomology, there is a thing called coefficient ring R. This is very similar. When you define a vector space, you will have a scalar field, right? So that is very similar to that one only. And once you have this coefficient ring, we denote this HIXR. This is the ith cohomology of X in coefficient ring R. So this is in red color. So I request you to remember this notation. I will be using it. So now let's see an example for that. So this is the space you see, it's a torus, we call it torus, and it is actually product of two circles. So you can see that, like if you take any point in the horizontal blue, for every point there you have a vertical circle in the red direction. So that's why you can visualize that this is product of two circles. And the cohomologies of these things are presented here, meaning this H0 represents the number of component of these topological spaces. So as we can see that this is one component only. Like if we would have taken 2 points, it would have 2 components, but it is a connected thing. one from one point to another, one can go easily within the space, within this, staying in this torus. So that is connectedness. So this means it is connected means we have only one. You see here. So the coefficient ring is mod 2 here. We can take anything, like we can take integer, set up the group of integers, we can take anything which is commutative ring with identity. So here we have taken this Z mod 2 group, sorry, Z mod 2 ring. And this H1 has two components, Z2, another component Z2. Red Z2 represented by the submanifolds, meaning these circles, all the vertical circles represent this component. And you see that any component, any two vertical circles in the red direction, that can be transformed from one to another without tearing it. That means they represent the same element in the cohomology class. So that's why it is like class of A, not by A. Similarly, for the B, if you take any two horizontal circles, one can be transformed from another, one horizontal circle to another. And then the two-dimensional cohomology class will be represented by this whole thing. This is, and there is no other two-dimensional cohomology class. And all other higher dimensional cohomology will be 0. That one can show. And in this commutative ring, this cup product, the ring structure, for the ring structure, the multiplication is commutative. And one can show this one also, like this. And if you choose a point, any point which represents a component of the space, this is the identity in the multiplicative structure. And if you take this vertical circle, two copies of this vertical circle, okay, so that, okay, if you take a vertical circle and you multiply with itself, that will be 0. I will show an explanation for in the later slides. So this means this A times A is 0, B times B is 0, and A times B, one can show that it is the whole torus. And this, and if you multiply torus with the cup product, it becomes 0. So now I will talk about the symmetry in the cohomology groups. So if you have a closed n-dimensional manifold, closed meaning it is compact and without boundary, and one can show that for such manifolds, one can have only surviving cohomology groups starting from H0 to Hn. Afterwards, all cohomology groups will be 0. So these are only interesting cohomology groups. Other cohomology groups are 0. And there are isomorphism. Like all the semicircles are isomorphism, you can see. The topmost is isomorphic to the bottommost. The second top is isomorphic to second bottom. In that way, this Hi is isomorphic to Hn minus I. This is a very particular statement of Poincare duality. It has very general statements also that I don't want to explain here. And so this Poincare duality, so these isomorphisms are Poincare duality isomorphisms. So if you take an element here, name it X, and the image under this isomorphism, the Poincare dual of X which stays here, we denote it by X star. Now assume two cohomology classes. So as you have seen in the last example in the torus, there are classes which was represented by submanifold, one-dimensional submanifold, which are circles. So we have seen that cohomology classes can be represented by submanifolds. So now assume that we have two cohomology classes represented by two submanifolds M and N. Then if you take the Poincare duals of them and if you multiply them, this M star meaning the Poincare dual of M, Poincare dual of N, and if you multiply it, it will be the Poincare dual of their intersection, the intersection of those submanifolds. So provided this intersection has to be transversal, means it has to be a very nice intersection, like X. So in that way, yes, 5 minutes left. Okay. So now I will talk about generalized Dold space. So it is. So you take a topological space and you take an involution there, meaning if you compose it twice, it will become identity map on S. If you can think of it, if you take S to be a circle and if you rotate it 180 degree, then this if alpha is 180 degree rotation, then it is a involution, because if you do it twice, you will get back to your previous position. And you can think that this has no fixed point, because every point is moved to its opposite point or 180 degree rotated point. And if you take another topological space X and an involution with fixed point possibly, there has to be a fixed point of course, then you can construct this S cross X and alpha cross beta. So I will give an explanation for that, like what is this map actually. Basically alpha is acting on S, it is understood I think. So this has no fixed point. Then you identify, so in S cross X, you identify those points, S comma X and alpha S comma beta X. Then S cross, then the quotient space of S cross X is called generalized Dold space. So the classical case is when S was Sm, the sphere of dimension M, and X was Cpn, the complex projective space, and the involutions were antipodal map and it is conjugation, complex conjugation. So we denote the generalized Dold space made out of S and X by PSX. So you see in this example, so if I take S to be a circle and X to be a circle, and here this is 180 degree rotation, meaning X comma Y goes to minus X comma minus Y, and here you take the reflection with respect to X axis. Then this alpha cross beta takes one point to the opposite side and reflected with respect to this green line. So this is alpha cross beta is doing, taking every point to its opposite side and taking the reflection with respect to green line. Then so in this torus, you identify all those pairs, like think of these two points as one point, then you will have some space that is a generalized Dold space, which is denoted by this PS1S1, and one can show that this is Klein's bottle, meaning if you identify those points, you will get this Klein's bottle. So similarly, we had S1, now we have Sm, and similar map like going to X going to minus X, and here reflection with respect to the last coordinate. Then we will have this PSM PSN, which we denote in short by PMN. 1 minute. Okay. So then we have this ring structure. So then we can compute the ring structure for that. That is this. So P11, as we saw, it was Klein's bottle, and it can be shown that it is connected sum of two copies of two-dimensional real projective spaces. So similarly, one can show this one, like PM1, it is RPM plus 1 connected some RPM plus 1, and one can show that the ring structure is this one. And So I don't have time now, but yeah, so for n greater than 1 cases, we have the ring structure is this one, where A is the ring structure for RPM. And this is an example which is this is just done in more general case in our paper here. And here we have computed the ring structures for generalized Dold spaces in much more generality. And this is the work done with Parmeshwar and Sankaran. Yes. Okay. Thank you.